Welcome to the Manzanita Institute's third Institute event of the 2017-18 school year. We're joined by Adam Wess, who is a math educator and founder of HOME, the Heart of Mathematics Education. He works both with students and with adults, teaching intuitive mathematics, which I'm going to let him tell you about.
Hello, everybody. I was enjoying how everybody was talking about math recreationally while I was trying to get the animations set up. So awesome. It's an honor to have people who are either love math or have an inspiration to find out a new way to love math if it hasn't resonated with them yet, which is actually quite a common thing, of course, right? Everybody, math is hard, math is, not for me. Just today I met a girl in the park and I told her I was doing this talk and she said, oh, math was never me. I got straight A's but not with math. And the reason for this, and she was attributing this to her own aptitudes in mathematics. But the reason is more a cultural one. And one of the reasons is we disconnect from the experience of mathematics. We make it something where you get the right answer, you use it. It's very utilitarian. And that's a reflection of our culture's values. Do this to get something. It's very motive-oriented. But math can be something where you subjectively, you have a subjective enrichment. You get to enjoy a beauty, a greater abstract awareness around you. And that is what intuitive mathematics is all about. Intuitive mathematics is all about seeing math through the lens of the senses. Math is purely abstract, but when we look at it visually, if we can find a way to visualize math, then all of a sudden we're experiencing it. And there's a lot of years of math that people do, but really between arithmetic and calculus, there's only so many very distilled concepts that if you really master them and embody those truths, you become, well, just profoundly good at math. So this talk is about 3 ways to realize your mathematical genius and start doing math intuitively. So there are 3 ways. And let's see. So the first thing I wanted to show you guys, which I wanted to put on the board, but on the screen, but I won't be able to because of some JavaScript issues. But I have this cube here. And I want to just kind of show everybody this cube. You see, it's a cube. And it comes together, and it splits apart. Can you guys see this? I'm going to let you guys kind of stare at it for a bit. My initial plan was to sit and meditate for 5-10 minutes while you guys walked in and have this on the board, on the screen. So it's really something you can contemplate and sit with. So how many pyramids, what do you guys think? How many pyramids come out of this? Oh, and are they pyramids? Do you see that these are kind of a pyramid type shape? And how many are there?
3.
3, okay. So in math we learn an equation. Does anybody know the equation of a cone or the equation of a pyramid? Anybody know? You know why you don't know if you had taken a class that taught you that at some point? Because you don't retain something that is not connected to experience. Everybody knows that the ocean is blue if they've seen the ocean before. But you may not know the ocean was blue if you read in some obscure sentence in a book at some point that it was blue, because that would be pure memorization. So mathematics is about comprehension, not memorization. And when you do it through memorization, you may be able to get answers, but it's very dry and you're not connecting. When you comprehend math and you see the truth of it for yourself, then like with this cube, actually I'll put it on the floor here. So with this cube, we can see that 3 pyramids make up a cube. And the reason for that is we've got 3 dimensions. And actually, I'll show you guys. So if I have a cube here, imagine a tiny little cube that starts, say, in a corner. Call this the corner. Imagine that's the corner of a room, okay? And if you've got a cube in the corner of a room, it's going to grow out at you. So as it grows out, it gets bigger like that. Right? You guys see that? So this cube starts in the corner. This is in the background. And as this cube grows, it starts from a point, and let's just imagine this little square right here. This corner goes all the way up to that corner right there. This corner goes across the cube to that corner right there. And this corner goes over to this corner right here. And so what we get is a square coming out and growing. And that's exactly what a pyramid is. A pyramid is a whole bunch of squares, like almost imagine you cut out pieces of paper, and they're all squares, but they're changing size. And they get, say, from a big square to a small square. So the cross sections of a pyramid are squares. It's really the sum of squares, which is a really interesting thing we can see in arithmetic too. So this one face right here makes a pyramid. It literally grows out and cuts a pyramid. Now, I know this, I'm really throwing, like, we only have an hour and a half, so I want to show you guys a few things. And without much feedback, I may be going too fast, I may be going too slow. Does anybody, especially kids, see what I'm talking about or have a question about it? Or maybe, think of this workshop or talk as a guided contemplation. We're contemplating, yes?
So what I'm thinking of is, if you're telling me that a pyramid is just stacked squares of varying sizes, then that point on top is not actually a point, it's a tiny, 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 tiny square.
I like that. Yes, an infinitely small square,
Okay.
which is a point, because it's not an infinitely small triangle, it's an infinitely small square. I like that. I actually never thought of it that way. It's a very good point. Yes, yes. So, does anybody else want to add something? I like your enthusiasm. You're very like ready to be here. What do you guys think?
I see it.
You see it? That's the kind of feedback I'm talking about. Thank you. I see it as good, or I don't see it as good. Any sort of feedback like that is great. So, okay, so now, how many of these faces are there? There's a face there. There's a face on top. Right? So that face grows up to these four corners, and it makes a square. So the point of the pyramid is right here, and the baby squares happen at the bottom, and the biggest square happens up here. So we get a pyramid there, upside down. We get a pyramid here that's coming to this space right here. And then we get one more pyramid, which is in the back there. It's like a face back here, and it grows out to this area. Now, I actually meaning to create an animation that shows this growing instead of just showing the finished cube. But this is a way to see why that happens. And the reason it's 3 is because we've got 3 dimensions, where if we hold one dimension, if we move through one dimension, so if I move through one dimension, I've got 2 more dimensions that I can move in. So I've got a square in 2 dimensions moving through a 3rd dimension. So we've got a little baby square, which is 2 dimensions, moving through a 3rd dimension. So we've got, each dimension does that. I can move this way with a square, I can move up with a square. And so in 3-dimensional space, a pyramid will have, 3 pyramids can make up a cube. Yes?
Question.
Yes?
Why only 3 faces? Why not all 6?
That's a beautiful question. Now, so the thing about intuitive mathematics is you can do it any way you like. There's no right way. So I thought to myself, why is this true? I saw an equation actually. Actually, you know what? I didn't see an equation. I'll get this. I happened to stumble across this just contemplating, and I'll get to why that's so important. It's in this case, it's not 6 because if it was 6, we'd have to All right, so we could do it with 6. If we started in the middle, we could actually make a pyramid, a pyramid, a pyramid, a pyramid. There's different ways that we can actually see how pyramids fit into cubes. Now, since the square is going from a point to a square, we do create 6 faces. See, this face and this face both have half triangle faces on the side, which make. Okay, so let me try and show you. So we've got this. Here's one of our pyramids. So if I draw it again, Now, because of the angle, it's not totally easy to see that this is a pyramid unless I maybe draw some squares for you. So you see there's squares growing up in the background here to become a pyramid. So do you see this pyramid? You guys seen it now? Yeah. Okay. Yes. So we have a bottom, which is a triangle, right? This bottom is a triangle. The side here is a triangle. And then we have a square face. And then we have another triangle in the back, which is a different shaped triangle. So this triangle and the cube that's on top here, see, I'm going to draw another cube. Now do you see I've got my little square right here, a bigger square right there, and we grow another pyramid with this little point here. It makes a triangle here on the face, and those two triangles, it's not perfect, those two triangles make an extra face. So you might say, well, if it's making a cube, we've got 3 faces, but really we have 6. We do have 6.
Now I see it, because what you're doing is you're using one triangle from one pyramid connected to another triangle from another pyramid to make those other 3 faces.
Other 3 faces, exactly. And if anybody has a 3D printer, I would encourage you to create this, because that would make it really easy to see it, right? You could literally take it apart. Now, if you're not totally seeing this is okay, because this is something that you think of it as an impetus for contemplation. You eventually will see it. Now, let me show you the 2-dimensional analog of this. The 2-dimensional analog is if I have a little baby square in the corner, and the square grows, what does it make? A triangle. 2 triangles, exactly. 2 dimensions, 2 triangles. 3 dimensions, 3 pyramids. 4 dimensions, in fact, this is a little harder to think about and see, 4 pyramids. And those are a different kind of pyramid. It's this is a 2-dimensional pyramid, it's a triangle. A 3-dimensional pyramid is a pyramid. And then there's a 4-dimensional pyramid, which is, call it a hyperpyramid. So we can see how this growing square has this 1 dimension growing through from a point to a line, and that makes a triangle. So a triangle is actually a sum of consecutive lengths growing make a triangle. And with a pyramid, squares growing make a pyramid. You guys see that? So now I know we've got very young people in this class, and we've got some veteran teachers, and so this may be a little challenging for some people to see, but it doesn't matter if you totally see it. What matters is that you start seeing it, because intuitive mathematics is not something you complete. See, the way I came across this is, see, what are we doing here? We're counting something. It's a form of counting, right? Mathematics is all about counting. It's about quantification. So we want to quantify something, but in order to not be quantifying as a motive for some results, in order to enjoy, when you go salsa dancing or surfing, you don't go to get the result. You go to experience the act of those activities. Well, the act of mathematics is quantification. And so the first way to realize your mathematical genius and start doing math intuitively is to engage in the essence of mathematics, which is counting. Now this goes to, when we're counting in, actually, you know what? Let's pull up a couple things up here on the screen. So there's all different types of counting. In calculus, we're counting something a little more exotic. In arithmetic, we're counting pure quantity. What?
I never thought about a pyramid being like that, just a bunch of squares that were kind of piled up and made smaller. I said I never thought about pyramids like a bunch of squares, but when you show it, it makes a lot of sense, because it starts out as a square on the bottom, and you're building it up.
Right.
It's squares on top of squares.
You know what's interesting about that? So we're counting, say. What do you guys think? So you're tapping into something I'm going to show later, and if I show it in this order, it'll give away. Well, okay, so let's try something. Let's start with counting. Does anybody know? So there's this famous story. Does anybody know the mathematician Gauss? Anybody heard of him? Gauss is the kind of an Einstein of mathematics. Yeah. Okay, cool. So in the 1800s, Gauss basically was they say he's one of the best mathematicians ever, and probably the best since antiquity. So Gauss, apparently when he was a kid, and this is a fable, maybe not true, but I like it. Somebody asked him in class, what's 1 plus 2 plus 3 plus 4 plus ... all the way to 100? And he got it in 10 seconds. How did he do that? Does anybody, actually, you know what? Go for it, guys. When you get it, we're going to have to... I'll give you a hint. Try to do it in a savvy way. If you just count, it's going to take a long time. Think of a... Yeah?
1,000?
Not 1,000, but I like the confidence. That's great. Can we look at this like a triangle? This is actually very triangular. How is it triangular?
There's the point, and then there's the square.
That's the point, and that's the point and the line, right? Because this is growing like, I could say it's 1 little square plus 2 squares plus 3 squares plus 4 squares plus 5 squares plus 6 squares, right? You see how I'm making a triangle here? And then I'm just going to go, and it's going to go on. So the area of this staircase kind of reminds me of Mario Brothers 1 when he's walking up the stairs, right? There's like what's the area of the staircase? Well, it's hard to find the area because it's not a square or a rectangle, right? But you can see that if I said, here's a square, here's going up like this, all the way up to 100.
And there's 100 on the bottom.
Yes, this would be 100 wide because here's 1, here's 2, here's 3. You see that's 3? 3 squares, 2 squares? I'm literally counting squares. If you connect math with counting, it's pretty easy, right? Everybody knows how to count. But when we get all obscure and make things ethereal, it's hard to connect with it, and you don't have that confidence. You want to be your own authority. There's nobody to talk to. Consult with the universe when you do math, not with your teacher or some book or the internet. You can ideally, your teacher would help you to have a conversation with the universe directly. Yes?
500.
Okay, so let me ask you this. 100 plus 99 plus 98 plus 97 plus 96. That's almost 500 already.
Oh, you're right.
Right?
Yeah.
So what? 500,000?
A squared plus B squared equals C squared.
You know, there's a beautiful way to see that one to directly see it. But okay, so here, so we've got 100, and then what's your name?
Bob.
Bob. Bob is a great student so far. Bob saw that there's 100 stairs, and I think he would have gotten to the fact that there's also 100 tall, right? So this is 100 by 100. Now, let me ask you guys, so here's one thing that I do with my students when I'm sitting with a student, and I'm not able to do this in this group format. I'm not able to do it in the group format because I can't engage directly with everybody, but at one-on-one. But really what we want to do is we want to isolate things. And I'll do it with Bob. Bob, and you guys can watch. How can I find the area of that? Well, we know it's 3, right? Like
Okay.
it has an area of 3.
3 units.
3 units, okay. So, but isn't it true that if I doubled this, duplicated it, and put it on top of itself, we'd have a rectangle? Here would be the duplicate rectangle. We'd have this bottom one and that one. So 1 plus 2 is the same thing as, so I could say 1 plus 2 which is this little guy and these guys, if you doubled that, 1 plus 2 again, that equals 2 times 3. Do you see why it's 2 times 3? 2 wide and 3 tall? So, well, we know that 6 divided by 2 is 3.
Or 3 times 2, because you've got 3 sets of cubes in the bottom one and 3 sets of cubes in the top one.
Right.
There's
Or-
2 3s.
Or
Same thing.
3 2s, you're saying?
Yeah,
Yes.
or 2, yeah.
Yeah, both ways. That's a whole awesome point with multiplication. Multiplication actually is commutative, right? 2 3s is 3 2s, and there's different ways to intuitively look at it. So let me do a bigger number. What's your name?
Alexon?
Alexon?
Alexon.
Alexon.
Yeah.
That's a cool name. Okay, Alexon, let me ask you this. If I've got these squares, how many squares is that?
6.
That was pretty easy, but
Yeah.
do you see that if I duplicated it, that would also be 6, right?
Yeah.
And that would therefore be 12 total squares.
Yeah.
Now, what are the dimensions of this rectangle?
3 by 3.
3 on the bottom?
And 4.
3 by 4, sorry. Went too fast. So 3 times 4 is 12. And what's 12 divided by 2?
6.
And you can see it. You're like, Adam, why is he showing me this? It's so obvious.
Yeah.
We want to make math obvious. It's ridiculous how obvious some of the things that I learned in college that I did not understand at all and forgot on tests, how obvious they are now to me. Like, it's like, why didn't they just show me this? Just show me that the derivative of sine at 0 is 1. I'm going to show you guys that. It's just so obvious. It's calculus, but no matter what age you are, if you're looking at the picture, it's absolutely true to you. And that's what math we want it to be, I like to say, incontrovertible. To you, it's incontrovertible. You can't deny it. Incontrovertible and self-evident. So it speaks for itself. So let's do another. So does somebody want to do, so this is 1 plus 2 plus 3, right? What's 1 plus 2 plus 3 plus 4 plus 5? 1 plus 2 plus 3 plus 4 plus 5. So you see, we just have a bigger staircase. Now, how wide? So now we could add them all up like you're doing, Alexon. Right? You're just adding each one, right? Are you?
Yeah, kind of.
Well, let's use this kind of savvy trick. What if you just, and I call it a trick, but it's not really a trick because we're still counting. We're just seeing more quickly. Put it on top. Okay, so the area of this rectangle is 2 times the area of that staircase. Yes?
Is the answer 5,000?
For this?
Yeah.
You're so close. So close. Very close. How did you get 5,000?
We did it together.
Are you guys related? No?
She's my teacher.
Oh, okay. Makes sense.
But tell them how we did it.
How did you do it?
Well, we did 100 times 100,
Mm-hmm.
and then we divided it in half.
And why did you do that? That's actually pretty much the answer.
That's
But
what you're doing with the smaller square.
except for,
Plus 1, right? 100 times 101.
yes.
'Cause there's
Would you like to take it away, sir?
There's an extra square on top.
Yes.
Because there's an extra square on top, the upside down staircase on top, because it starts with 1.
See, this is 5.
Yeah,
Right.
because there's a 1 all the way to the left, and when you flip it over, there's 1 more on top of the far stack. So then the height becomes 1 more than what you have on your bottom staircase.
Exactly.
Huh?
So look, this wasn't 3 times 3 divided by 2. 3 times 3 is 9, divided by 2 is 4.5. That's not 6, right? It was 3 times 4 divided by 2. This one was 2 times 3 divided by 2. And this one is 5 times
Okay.
6 divided by 2. You see, actually, when we put these staircases together, the top staircase actually sits on the bottom stair. It doesn't touch the ground. And if it does touch the ground, it gets wider. We could do that too. We could say something like this. So there's 3. We could put it on the side like that, in which case this is 1 wider, 3 and 1, and 3, so that's 3 times 4 sideways, right? So, do you guys see this? This is a good one to get. If you get this, you're going to see, today's talk is really about, for you as individuals, think of this as a chance to make a paradigm shift. So you make a paradigm shift with one thing, it'll change everything. Because the way you do anything is the way you do everything. So, if you throw away your garbage with gratitude, you probably, talk to your mother with gratitude, right? So if you do mathematics intuitively with this, you'll be able to say, hey, let's do it intuitively with everything else I learn from now on. Right? And how old are you?
I'm 10.
You're 10. So you've got probably many, many years, hopefully decades of math. See, you want to keep doing math. Math strengthens your mind. It's not just about, oh, I don't need to do math. I'm not balancing the checkbook. Math, you do math, I get high on math. I get so clear. I walk around and I feel my forehead, third eye just beaming with energy. I mean, it's a great way to cultivate your state of mind. So decades, okay? Okay. Okay, so now, 100. Now, so we're going to take this 100, and we're going to, so this is 100, and we're going to step it on top. So now it's literally 100 wide, and how tall is it?
101.
101. And what's 100 times 101? Well, this is another thing we can do intuitively. What's 100 times 100? 10,000. And 100 times 101 is therefore 1 more 100. 100 and 1 hundreds. 100 hundreds and 100. Right?
10,101.
Except for the last one.
Why 1? 100 hundreds and just 100. Now I'm going to give you $100 bills. Here's $10,000. And I'm going to give you $100 more. That's another $100 bill, right? So 10,100. Didn't do any $1 bills in that transaction, right? Yeah? You see, the $100 bills worked for you. Okay, so.
Because you have to multiply that one extra piece times 100.
Right.
Yes. You know, I'll show you something here that's interesting. 100 times 100 looks like this. Right? If this was 100 little squares going sideways and 100 going this way, how many squares would there be there? 10,000. Now, if I said 101, what's this top little layer here? 100 little squares. So we've got 10,000 here, 10,000 there, and 100 here, and that's 10,100. So this is an intuitive way to connect with what we call the distribution property of multiplication. And rather than just saying A times B plus C equals AB plus AC, which makes, it makes sense, but it's not very intuitive, why. There's a whole bunch of unknowns going on there if you're brand new to math, but anybody can look at this because everybody sees carpets and walls and areas in front of them. So you see, this is the intuitive version of that. We're visually experiencing it. The visualization can provide a window through which we quantify. It's the window of quantification of area. If we can see either area or objects, then that's one way to map quantification from the purely abstract realm into the experiential realm.
Quantification means counting.
What?
Quantification means counting.
Yes. Oh, yes. You guys are going to walk away with a bigger lexicon. That means vocabulary. That means, yeah. Okay. So we've got 10,000 over here, 10,100, and now we're dividing it by 2. And what's 10,100 divided by 2? Let's hear from a kid. You got it.
Okay, I think it's 5,050.
5,050. We've got another Gauss in the house. That kind of rhymed, huh? Gauss in the house. Okay, so 5,050. So 1 plus 2 plus 3 plus 4 plus 5 plus 6 all the way up to 100 is 5,050. Okay.
Intuitive.
What?
Oh, Bodie was only 50 off, and he said 5,000.
Right, right. Yeah, because the interesting thing about this is when the numbers get really, really, really big, these little jagged edges of stairs become very inconsequential. Down here, 3 times 3 divided by 2 is 4.5, which is not 6. 3 times 4 divided by 2 is 6, right? But if I do 1,000 times 1,001 divided by 2, it's almost 1,000 squared divided by 2. So when numbers get really big, these little jagged edges, which are not quite the right area, not quite the area of a triangle, become inconsequential. And when this is infinitely big, when we're counting to infinity, those don't matter. It becomes, well, let's say infinite resolution. Basically, if we're adding in a linear way, it does become like a triangle. So this is a triangular way to count, triangular counting. So when we engage in the essence of counting, of mathematics, which is quantification or counting, we start to see these things. So now the beautiful thing about what we did here is the whole process was the answer. The answer wasn't just at the end, right? We got to look at specific examples. We did counting, and now we've focused our minds in this way. And so really, the second way to realize your mathematical genius and start doing math intuitively is to explore organically. So organic exploration. Now what makes it organic? No motive. There can't be motive. You do it because you're seeing mathematical elegance. You're seeing something in the math. So motive is something that causes conflict within us. This is a spiritual principle in yoga, for example. We don't want to do things for the results of our actions. We want to do them for the actions themselves. And when you do it for the actions itself, you awaken the greater creativity, a greater presence in your being, and you do more. So now what do we have? Okay, so let's look at something. What if we did this with a cube? Now it's a little bit harder with a cube, but with a cube, we're going to have little funny stairs, but the stairs are going to look like kind of a coliseum of sorts. Let me try and draw it for you guys. Can you guys see this, by the way? I know it's quite small.
I'm thinking that it's going to be really important to think about layers.
Layers? What do you mean?
Well, because if we're doing this for something three-dimensional, I know that when we do volume, if you can figure out what the area of one layer is, and then you can just stack that and look at the height, then you can figure out the volume of a cube.
Right.
So I'm thinking that if you can do essentially the stair-step two-dimensional problem for each layer getting smaller, then you're going to get the same kind of answer.
You're beautiful. We can actually fit these together to make some sort of rectangle, I think you were getting at, right? Because a rectangle is a bunch of layers. They're all the same layer, right? And length times width times height gives us. The thing is, to fit these together like a rectangle takes 6 of them. And one of them has to be split up a little bit. And it's actually, it's quite hard to see in your mind. I could try and show you guys, but let's first look at it qualitatively. So if do you see this shape? And it has stairs, so it's not really a pyramid, but if we make a lot of stairs, it starts to be really smooth, right? Imagine they're little baby tiny stairs. From far away, it just looks like a pyramid, right? So the question I could ask you, you know what? A question I could ask you is, what is 1 plus 1 squared plus 2 squared plus 3 squared plus 4 squared, and so on, up to 100. Now this number is 100 squared. See, this is the first layer is 1 squared. Then we've got 4 underneath it, 2 squared. Then we've got 9 underneath that, 3 squared. So the volume of this pyramid thing will be the sum of consecutive squares. Now this is what you noticed earlier. You actually may have guided the whole talk in this direction because that was a good insight and a natural thing for us to talk about, which is that, isn't that interesting? The sum of consecutive squares is a pyramid. That's the nature of a pyramid if we're counting volume in a pyramidal way. So, okay, so now you guys were really close, right? You said, oh, he was only 50 off, right? Well, let's just pretend we want to get to that, like, 1,000, 100 times 100, it's 10,000 divided by 2 is 5,000. That's pretty close, good enough. We don't have to do this extra 100 here. That confused things. And with this one, it gets a little bit more confusing. You guys could totally do it, but just because of time constraints, I think it would be cool to look and see if we can find the approximate value. Does anybody have an idea? What is the approximate value of 1 squared plus 2 squared plus 3 squared all the way up to 100 squared? Now you could, if you guys are seeing this, you could do this in your head very quickly, very easily. And you can even tell me as a fraction if you like. Here's the hint. 3 pyramids make a cube, right? And each of those pyramids is a bunch of layers which are consecutive squares. So if we could find the volume of, think of this as 3 of these make up a cube, which is 3 by 3 by 3. Do you see that?
Okay.
Yeah?
So what I'm thinking is, now I'm just trying to visualize how they fit together.
You want to do that?
Because
we could try that.
It feels like you're going to have 101 times 101 times 101.
It's close. I like. You're right. It has to be 1 because we take this thing and
Put
we
it
kind
together so there's 1 on each.
Yes. Okay. So the way I drew this doesn't really. Well, okay. I want to give you guys the general estimate first because that part is pretty tricky and I don't want to lose everybody. Because if I go too fast, I'll lose you guys. And it takes probably about 20 minutes to get it right. So this, if we zoom out, this just looks like, doesn't this just look like it's like that pyramid thing. And it's not an actual pyramid, it's I think you call it a right pyramid because it's kind of all against the wall, right? So the back part is kind of like you could fit it in the corner of the room, right? So 3 of these, because I showed you this animation, right? This animation showed us that 3 of those makes a cube, right? Now, what if this cube, the square part of one of these pyramids is 100 by 100? That's the biggest part. That's the last one we're adding, right? So the point is 1, and it goes all the way up to 100. And therefore, what's the volume of this whole cube? It's 100 times 100 times 100, right? Now, it's not actually that. It's more like 101 times 101 times, so you're right. But let's just imagine this is 100 times 100 times 100 as an estimate. Then what's 100 times 100 times 100? A million. And one of these pyramids would be our sum. So, anybody want to do the honors and say what it is? What?
333,333.
That is correct. So if I added all the perfect squares between 1 and 100, it would be about 333,333. And it's actually very, very close, just like your 5,050 was very close to 5,000. You guys see that? Now, okay. So now, so there's a structure in counting these consecutive integers or consecutive squares. There's kind of like a nature to it, right? It seems to be behaving in a particular way. So what about if we generalize it with some sort of statement? And you see there's 2 things. There's the language of mathematics, which is what most people learn. And then there's abstract truth or mathematical elegance, or I've been looking for a number of words that describe what it is. It's the form of quantification. It's something abstract that has form. It's inherent to the universe. There's that, which you cannot describe. Once you describe it, you've kind of looked at it in a particular way. It's like looking at love. As soon as you write a poem about love, well, it alludes to love, but it's not love. So any equation alludes to the truth, but there's something about it that is irrational. Who said that? Was that a joke? Because irrational numbers. So there's something about it that is irrational, or it is logically sound, but what it's doing, it's obscuring the truth because we're looking at it from a certain angle. And whenever you look at something from a certain, the only way to truly know something is to be it without describing it. This is another yoga concept. This is kind of like yoga of mathematics in a way. When I say yoga, I don't mean yoga positions and movements. I mean the spiritual practice, the philosophy of yoga. So let's look at this and find the generalization, which is our description of it. It's going to be pretty close to the actual truth. It's one way to look at it. We said, like, if I asked you, what is the sum of the numbers between 1 and 1,000? Can somebody just tell me? 1 and 1,000. Just regular numbers, not the squares. So it's like, I know Bob can do it. How about you guys in the back rows? This guy's a math teacher. I want to hear what he thinks.
Well, I'm just trying to observe, and see what's going on here. But
Cool.
For me, I would start comparing it and start thinking about, well, if I figured out what the sum was between 1 and 100, and I would start looking for the relationship between what it is between 1,000, and I would think of it that way.
Right. Okay. So if we had 1,000 here and 1,000 here, it would be 1,000 wide by 1,001 tall. 1,000 times 1,001 is 1,001,000. 1,000,001,000 divided by 2 is 500,500, right? So, okay, I could do the sum of the numbers between 1 and 10. You. I know you're up for it. Sum of the numbers between 1 and 10. Picture this. How are you going to wow people at your next party? You can do it. I'm up here all by myself. You're over there. Come on, you can do it. You sure? Would you like to do it?
I can't.
Well, guys, look at this. Look at this. What about you guys? What if both of you come up here? Can you both come up here and draw something for me? You guys can do it together. Hold hands.
He'll help you.
So, and you, because I said both, right? Look,
1, 2.
you got to be fair. Yes. Okay. So, 1 through 10. 1 plus 2 plus 3 plus 4. Draw a little staircase. A little one of these guys. Draw one on top of itself, and see if you can see intuitively why the sum between 1 and 10 is what it is. Eventually it gets a little tedious writing every square. You can do it if you want, but you can also just write columns, right? So now without adding them individually, let's pop one on top of itself, a duplicate. Okay. Now how wide is it and how tall is it? So we have a rectangle, right? And you know how to find the area of a rectangle. And we know that the rectangle is twice as much as we were looking for, right? Because we want to know just the area of that staircase, not that one. So how wide is it?
10,
How tall is it?
11,
Nice. So what's the area of it?
1 and 2. I know.
What's 10 times 11?
I know. Oh, 10 to 110.
110, yes?
55.
Very good, very good. Somebody in the audience already got to it, but you guys can get it too. So we've got 110.
Yeah.
And what's 110 divided by 2? There you go.
Oh, okay.
So you got it. Good job, guys. And you were great support. Yes. Good job. So, okay, so now what if I wanted to do it with an arbitrary number, some random number? Because we could pick any number and just practice this forever. But what if we wanted to kind of say, what's 1 plus 2 plus 3 plus 4 plus ... plus x? Well, the answer is going to have x's in it, right? So how wide would it be if it went all the way up to x? Yes, and how tall would it be?
X plus 1.
Yes, it would be x plus 1. And what did you do to the x times the x and the x plus 1? How did you get 110?
Multiply.
You multiplied it, so you said x times x plus 1. And then how did you get to 55? Divided by 2. So that is the third way to realize your mathematical genius and start doing math intuitively. It's to codify into the language of mathematics, subjective codification. This is code, like a computer programming is code, right? We're turning the numbers into a code, something that is a generalized expression of this intuitive insight that we have, right? So watch this. What's 100 times 101 divided by 2? 5,050. What's 3 times 3 plus 1 is 4 divided by 2? 6. What's 1,000 times 1,001 divided by 2? 5,000, 500,000, 500. You see, it answers every question at once. You got it?
That makes so much more sense.
I love it, love it, love it. Isn't that
Yeah, it's crazy.
paradigm shift, everybody? We have a paradigm shift over here. So what you've just done is you've glimpsed mathematical elegance, abstract truth. Aliens would do this. If they're aliens, they are probably know about this. Now, they may not write it this way. They may not have parentheses and plus symbols and all that kind of stuff. They may not even write it down. But they probably, if they're very intelligent, they probably are aware that the sum of consecutive integers behaves in this manner. It's like so when you look at this, you don't see symbols. You see length times width divided by 2, right? You're seeing it, what it actually is. You guys should see his face. He's got a hand on his face right now. Awesome, awesome, awesome. So, okay. So now to get to your inspiration. So if we want to take this, you see we fit these two to make a rectangle. We can fit 6 pyramids, not 3. 6 pyramids make 2, like a taller rectangular prism. So it's really hard to fit them together, but I'm going to just kind of show you. So if we go sideways, so here's a square, and it's like this. And you see the slabs are going to be standing next to each other, and it's going to go like this. You see, we're getting kind of a sideways pyramid. If you take this sideways pyramid, if you take it and you put it next to another one, it's going to be 1 wider because the stairs fit in that way. Now, what happens though when you put one on top of it, it's going to be 1 taller, but we get an extra kind of hole. It doesn't fit exactly. So then what we do is we do it again, and we get this on top of that. So it's kind of like we have this fits with, it'd be really tough to draw.
I think I need some Legos.
Yes, Legos would help. Yeah. So basically, we fit 3 of them with each other. One going this way, one going down, one going out, and then there's like a little extra space, and so we have to do another one on top. And then what's interesting is when we put both of those together, we get 6 of them, but some of them fill in that space, and we actually get a solid rectangular prism.
Where does the space come from? I don't understand where the space comes from.
We'd have to get some Legos. It comes from the fact that, okay, so you take two of these and put them next to each other. Then what we get, so imagine this right here. This is the one next to it, right?
Okay.
So we're fitting in here is the corner of the second one. You see there's and then we get this face right here. So what we've done is we've got this one grew out, and all these center steps kind of closed in on each other.
Got it.
Now we're going to take another one and put it, see,
I understand, because you have to put because now you've got two stacks together, and so you can't fit the other one right in there because you've got.
I know how I can show you.
Okay.
So okay, let's see. Let me get it in my mind for a second. Okay, so from a top view, I'm going to isolate. From a top view, we have this is the bottom of one of these. Okay, and now it's the bottom. So here it goes up, right? So this comes up, like put them on stacked up out of the page. Okay, now we have another one that is. You see, this is actually. Oh, it's tricky. What happens is we get like two squares, and only one of them fits in. So over here, what happens is it doesn't make a full. You see, there's 1, 2.
Sure.
So what we want to.
Really, but I'm thinking like I'm going to go home and play with Legos because I have to see it.
Yes,
now.
you could
Like, you
spend
made me really curious.
spend a week looking
Want
at
to
this.
see it, yeah.
Yeah, that's beautiful. That's exactly. So here's like a hint for you. So you see how there's 2 there? Well, when you put the third pyramid in, that point of the pyramid only fills one of them. So we're missing a whole wall that's triangular shaped.
Okay.
That's where that extra problem happens. Now when that happens, do you want me to tell you how you're almost right, or do you want to know it, or do you want to try to discover it? Or I knew the equation before I actually knew it. The equation was my impetus for exploration, which is okay.
Yeah, I think you should tell us.
Okay, so the bottom is x, and then this becomes x plus 1, so you're right about that. But then the height is now
X plus
2x plus 1. We get an extra layer, and it's 2x plus 1, and 6 of these make that. So x times x plus 1 times 2x plus 1 divided by 6.
2. Because you have 6 of them.
Because we have 6 of them. 6 of them come together to make that. And that was when I saw that, I was like, oh, this is cool. It was pretty cool. Because this is an equation you use in calculus. You generally learn this in calculus, but you just are told this equation. Now, you may have a proof for this equation, but generally you don't see, I've never seen you, in all the kids that I tutored over many years, and I got a degree in physics and did math all through school. I never saw this until one day I was sitting at my dining room table and I was just like, wait, why is it 2x plus 1? Like, what? Why? And then the first thing I saw is, okay, it's length times width times kind of like twice the height divided by 6. Okay, that makes sense because it's twice here. 6 is twice 3. So it's kind of like x cubed over 3. Do you guys see that? This is almost, that was my point, x cubed over 3. So the exact thing is not 333,333. It's, right, that would be this approximation. It's actually 1,000 times 1,001 times 2,001 divided by 6. Let's just show that that's right. So let's add 1 squared plus 2 squared plus 3 squared. What is that? 1 plus 4 plus 9. Right? Okay, 1 plus 4 plus 9. That's 14. Okay, so we've got x is 3 times 3 plus 1 times 2 times 3 plus 1 divided by 6. So 3 times 4 times 2 times 3 is 6 plus 1 is 7 divided by 6. is 3. Well, we could cancel first, which I actually recommend. Let's cancel first. The 3 cancels with the 6 to get a 2. The 4 cancels with the 2 to get a 2. 2 times 7 is 14. Now I feel really confident. Now you see I just did this independently. I could have been sitting in the forest somewhere by myself, never having learned math from any sort of authority, kind of like, what's his name? Srinivasa Ramanujan from India. I don't know if anybody saw that movie about the man who knew infinity. He basically wasn't exposed to very much. He didn't even know what a whole lot of math that we had discovered was, and he was able to figure out a whole bunch of things, which was profound because he didn't use what they had learned from the past 100 years or so, or at least parts of it. So you could just sit in the forest and do this because you're consulting with the universe, and you can confirm it with a specific example, generalize it with an equation, right? So memorization is the antithesis of comprehension, because memorization is of the past. Comprehension is active. It's in the moment. We're actively doing something, right? You're engaging your mind. You're not just accessing some sort of memory. So if you memorize your times tables, you're not really doing times. You might as well be memorizing the name of some words in some language, right? It becomes a language almost at that point. So I like to make this distinction between memorization and having the faculty of mathematics. The faculty of mathematics is the capacity to do, in the case for multiplication, it's the capacity to multiply. Well, what is multiplication? So multiplication is really just a form of adding, right? So if I say, what's 11 times 11? It's 11 plus 11 plus 11 plus 11. And adding is just a form of counting. It's 1 plus 1 plus 1 plus 1 11 times. That's what it means to add 11. So really we're just counting groups of 11 and 11 groups of 11. Now, if you have that memorized, so I have a student, she's dyslexic and she can't memorize things very well. And it's such a great thing for her, in my opinion, because it forces her to cultivate faculties instead of memorization. And yeah, she may not get the best grade, she may be slower than everybody else, but she's slowing down to speed up. When you slow down and you actually see things, then you discover special relativity. You discover, right? Einstein took 10 years to figure out special relativity or something like that. I'm not sure the exact amount. So I want to show you guys one way to see 11 times 11 visually. And you can always do this in your mind. Now the black box is, see, what I've done is I said 10 plus 1 times 10 plus 1. You see it? So 10 plus 1 times 10 plus 1 actually makes 4 rectangles. This one's 1 wide, 10 tall. This is 1 tall, 10 wide. This is 1 wide, 1 tall. And this is 10 tall, 10 wide, right? So now can we look at this and say, well, this is 10 by 10, which is 100. This is 10 by 1 and 10 by 1, which is
10, 10, 20.
20, 10, 10, or plus 20. So 121. So do you guys see 11 times 11 is 121 visually?
Break it down.
What was that? Break it down.
Break it down.
Exactly. Now watch this. What do you think 12 times 12 would be in that same way? Now obviously you may have it memorized, but try to forget it.
100 plus 40, 20, 40, 20 plus 4.
Not 2.
4.
4, right. Do you guys see this?
Oh, I like the 4.
Isn't that cool? So what's 13 times 13? 13 times 13 would be 100 plus 30 plus 30 plus 9. 169. Okay, so for all of you who are cheating and memorize these things, what's 21 times 21? We don't normally memorize that one, right? Well, what is it?
42?
Nope, that's plus. Think of it this way. 20 is the big black square, and 1 more. So we've got 20 times, I'm going to hold this up for you guys. So imagine this is 20 and 1, and 20 and 1. What would be the black square? 400. 20 times 20. We could look at that as well and break that down, but let's just do this for now. What would be this long rectangle? 20. What would be this rectangle? And what would be this corner? Not 4, because it was 1 extra. It'd be 1 by...
6, 2.
No, so we said 21, right? 20 plus 1, 20 plus 1. So a 1 by 1, yes. So we'd have 400, 20, 21. 400 and 441. 21 squared is 441. What about 101 squared? We'd have 100 times 100, which you know, 10,000. We'd have 100 here, 100 here, and 1. 10,201.
I like this.
Isn't that cool? Now, this is just the beginning. You can do it 3-dimensionally. You can do 21 times 22, different sizes. You can do x plus 1 times x plus 1. What is that? Don't use FOIL. See, FOIL is like a weird... See, algorithms disconnect us. Algorithms, a sequence of steps that we use to get an answer, like FOIL, first, outer, inner, last. For everybody who knows what that is from algebra. What is that? Oh, that's what my teacher told me to do. So I could get a grade and be successful in whatever external motive there is.
Not cry when I see polynomials, you know?
And why would you cry? Because you're trying to do something that you're not genuinely doing. Yes, exactly. Once it becomes intuitive, people will like math more because
It's fun.
it's fun. It doesn't tax them emotionally. It's fun. So x plus 1 times x plus 1. Does anybody know what it is from this picture?
X squared plus 2x plus 1.
Exactly. You see that? So, is it pretty cool? Thank you. I know, isn't it awesome? I love looking at it this way because I learned FOIL in school. And FOIL, if you forget FOIL, you spell it wrong or, you aren't going to get the answer. But no matter what, you get the answer when you see it. Because this is incontrovertible, self-evident, abstract truth. See that, guys? Now we could do x plus y times x plus y. We can do x plus y plus z times x plus y plus z. There could be more boxes, right? Okay, I'm going to show you, since we don't have much time, I'm just going to show you guys a couple things. Can't the talk be 3 hours? So here's something fun. Oh, you know what? Just to give you guys a sense of quantity, for those who are interested, these are programmed in JavaScript. So they run right in the browser. So look at this. This is 62 times 62. And you can see that's 3,600 squares right there. So next time you guys look at a fence and see a bunch of squares, you can have a sense for how many squares that is. It's actually quite a bit of squares and not that big of an area, right? So we can say 62 times 62, just like that. 3,600, 120, 120, that's 240, 3,600 and 240, 3,840 plus 4, 3,844. 3,844. Did I get that right? I think so. 3,844. I believe so, yes. Okay.
Is this why I was better in geometry than I was in algebra? You could actually see it and it makes sense.
But I would say that is definitely something true. However, in trigonometry or geometry, it wasn't always completely intuitive. Let me give you an example. You see this right here, guys? So this is not programmed in JavaScript. This is using Desmos.com. I've just got some equations that I made here that move around. So this is a circle with a bunch of lines. And everybody can see what it's doing, right? And you just look at it more and more, and you're kind of more aware of what it's doing. You can see that line gets really, 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 really tall and really wide right there. Well, each of these lines, the length of them represents each of the 6 trig functions. Now, you know Pythagorean Theorem, right?
No. Oh, yeah, Pythagorean.
Well, these are right triangles, which means the Pythagorean Theorem. Now, do you know Pythagorean Theorem intuitively? That would be something to talk about as well, right? But if you just know, and say you know it or not know it, you can use it in this case to see that sine squared plus cosine squared equals 1. Or tangent squared plus 1 equals secant squared. All of those trigonometric Pythagorean identities from Pythagorean theorem are in this triangle.
That's great.
Isn't that sweet?
That's really nice.
Yes. Also, these triangles are similar. So you can see the ratio of corresponding sides in similar triangles is constant.
So what this tells me basically is that math teachers have been cruelly torturing their students for no apparent reason for decades, because this makes it so much more like relatable and comprehensible and even exciting to think about. And there is no need to memorize once you understand it.
Right, totally. In fact, you want to have, in Zen we call it beginner's mind. You want to be empty of memory and see it anew every time. If you see it anew every time, see, math, if you just use math, you don't transform. But if you experience math, you transform. And the transformation makes you very, very, it enriches your subjective experience of life. It frees your creative potential, right? You can say you're a dancer and you comprehend all of this math. It could change the way you dance. Say you're an engineer, obviously it'll change the way you engineer. And then the great thing about this is you retain it.
Yeah.
You know how, did you hear that sentence about similar triangles that I just said? I was not memorized. I was speaking directly, recreating that sentence in that moment. I was thinking, okay, similar triangles corresponding, and it came from comprehension, not from memorization. So memorization is the antithesis of comprehension, and comprehension is transformative. So that's just an example. There's so many examples. This stuff applies to so many things. I'm going to play this one for you. Everybody learns pi r squared, right? Well, here shows us pi r squared. People tend to like this one because it's kind of fun to watch it grow. So a circle can be cut into a whole bunch of slices, and those slices almost approximate, see these little, they're sectors because they're rounded, they're not exactly triangles. But when we get more and more of them, the triangles become thinner, and they actually do become triangles. At the infinite thinness, they actually become a triangle. So what we can think of is that a circle can be laid out as a whole bunch of little triangles, like spikes like that. Well, the distance around the circle is this line underneath. The height of this rectangle is the radius. And all of these are triangles. So circumference times radius is that, which is really two circles, because we need another circle to fit like two combs together, one on the bottom, one on the top. So 1/2 the circumference times the radius. That's the area of a circle. Now, you see, that's not the equation we normally talk about, because I looked at it in a particular way. 1/2 circumference times radius is the right equation, just if we take circumference and we say 2 pi r, then we get 1/2 2 pi r squared. 1/2 times 2 is 1, and we get pi r squared. So this shows you pi r squared. And I know I'm going through these really quickly because I just want to show you guys a few more things. Did it go really small?
Where's the pi part?
Where's
Where's the pi come in?
the pi? Oh, so pi. So the distance around a circle. See, here's the problem with pi. Pi.
No problem with pi.
There's not room enough ice cream.
So there's one thing I wanted to share with you guys that I haven't said anything about yet, but pi isn't necessarily pi. And the reason for that is, what?
Is because it's imprecise, because we can never actually calculate it. We can't get to this finite amount.
So that's one issue, is it's irrational, so it goes on forever. But in addition to that, it has human artifact. Human artifact is when you take the pure word of the universe, abstract truth, and you interpret it in your own way. You add things that are artifacts. They're extraneous. One thing we add when we say 3.14, what does the 1 represent? 1 out of 10. The 4 represents 4 out of 10 out of 10. So all of a sudden we have a base system in there. So pi 3.1415, I always, when my students come to me and they say, I know pi to this many digits, I'm like, okay, but do you really know what pi is? Because really, that's an arbitrary choice of pi. Here's...
What base system is it still an integer?
Well, it's not an integer. So here's base 2 through base 10. All different values of pi. So these, I had to calculate these from pi in base 10 and figure out, see look, 1.001001, that's pi in binary. So when you say, oh, I know pi, what is it? 11.001. Well, that doesn't sound right, but it is right. Because 0.001 is actually 1/8, which is the same as 3.125. So it's close. It's not, once you go forever, you'll eventually have the same thing. So pi, now, so pi right here is, so there's different values of pi. Do you guys see it's not actually, there's a human artifact.
It's not it's an idea that we represent with numbers in our base system.
Right.
It's not.
And another, well, I'm sorry. Yeah.
But it's just not accurate because...
Well, it's accurate, it's just got an arbitrary
base
presence in it, right? Now there's another arbitrary aspect. So pi, by definition, or one way to say what pi is it's the ratio of the distance around a circle to the distance across a circle.
So the relationship, just to put it in a word.
Relationship, yes. So if I take a circle and I draw this line will go around 1 time, 2 times, 3 times, and a little bit. That's pi. Pi is 3 point something. Really 3. In binary 3 is looks like that. Well, 3 is 3, right? See, even to see that's the thing. When I write 12, that doesn't mean 1 plus 2. In Roman numerals, it would mean 1 plus 2, because the Romans said x, x, 5, all those things, and they added the numbers. Right? So see, there's a whole bunch of human artifact in that. 12 is 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's 12, which could be one set of 10 and 2 more. It could be one set of 9 and 3 more. Right? So there's human artifact in numbers as soon as you write them down, pretty much. Even 3 is a symbol, right? But we know what they are. So 3, 1, 2, 3 times, and a little bit more. So, if you could teach this to a 4-year-old, and a 4-year-old could grow up knowing what pi is. If you take a string, put it around a circle, it's basically 3, right? At least 3 and a little bit not exact. Even that's profound to know. Wait, it's not exact? That's weird. Why is it not exact? The universe didn't make it that way. So, right? So, or assuming that it's just not that way, if the universe made it or not, it's just not exact. So here's it's pretty philosophical. So here's another way. I actually personally don't prefer this representation of pi, because I like to think is in 2 dimensions we're able to take something and rotate it. And when we rotate it, there's a relationship between the length of the arc and the distance and how much we rotated. The angle of rotation. So if I move my arm like this, my hand moves a certain distance, and oh, that's not me. So our interpretation of pi this way is very geometric, but this is more of a trigonometric way of interpreting pi. So in this case, see, the radius goes around a circle 6.28 times. So I kind of like that version of pi. 6 radiuses. Radiuses are half as big as the diameter. 1, 2, 3, 4, 5, 6, and a little bit more. So you see there's arbitrary human artifact in pi. It could be, 3.24. You could say pi is the ratio of the area of a circle to the area of the square in which it's inscribed. Or the square is inside the circle. You could look at pi any way you want. This would actually be another value of pi. All the equations would change, but they would mean the same thing. Right? So, all right. So this stuff goes all the way to very advanced topics in math like this, which I'll show you guys really quick. These are like ducks in water. And the wave goes through the ducts, and the ducts go up and down. Right? Now, the sharper the wave, the faster the ducts go, the wider the wave, the ducts move very slowly. If the wave moves faster, the ducts move faster. If the waves point to you, the ducts move faster. Right? So you see there's all these relationships. This is a visual representation of what we call the wave equation, which is something from differential equations, which is a special kind of calculus. And yeah, so this goes to very advanced math as well.
What would
Yeah?
you use this, like how would this knowledge be applied in the modern world? How is this used?
The wave equation?
Yeah.
Imagine this is a property of a function. So the function is, say that we've got a pointy function, okay? The pointy function is moving, and it see what makes the wave is made out of the dots. Like if I make more dots, you see? So what it does is it helps us to model the way the medium, or the thing through which the wave propagates, behaves.
Okay, so
Is that-
yes.
But what's an
So
actual application?
You could use it to model the way that sound moves through a rock.
Probably.
Or the way that like
Anything to do with a wave, actually. Yeah.
anything to do with the wave. So sound moving through air, or maybe sound moving through different kinds of gas.
Yes.
Right?
Yeah. Totally.
So sound would move differently through different kinds of gas because the gas has different densities.
Right. So these would be like gas particles,
Okay.
and obviously gas has a different kind of. It's a wave that's like pulse, like it's like planes of pressure, right? Comes out like concentric spheres, which is different to this, which is like a longitudinal wave versus a transverse wave. But yes, it's still a wave. And you can represent it this way graphically. Also, I would imagine, I mean, there's waves in electromagnetism, there's waves in quantum mechanics, there's waves in seismic activity, there's waves in everything, right? So there's just anything to do with waves. This helps us to model the wave. But this is not an algebraic thing. It says that the curvature of the wave is proportionate to the speed of the things is proportionate to the curvature of the wave, and the speed of the wave too. But it's actually speed squared, and that's another topic to discuss. Why is it squared? To make this, so this is Desmos.com. Yeah, and the way I'm doing it, if you take a look on the side here, it's just a bunch of equations. But the cool thing is I can have variables in the equations that are time dependent. I can have lists which do a whole bunch of equations in a certain way. So I highly recommend for all the teachers in here, teach your students Desmos. It kind of brings things to life. Make sure to use time dependent and lists, time dependent variables and lists. You can figure that out with the documentation online. So my business is called the Heart of Mathematics Education. HOME is the acronym. I teach intuitive mathematics. I work privately with students. So I do guided contemplations, which are kind of like a tutoring session. I'm also looking for any teachers or older students who are interested in joining the program to learn about intuitive mathematics and teach with me. So I also have a mailing list and do little workshops and things. I'm planning to have some classes coming up soon. It's outside on the bench there, so if you put your email down, I'd really love to keep in touch and have you be part of it. It's such an honor to have all of your attention for so long and to meet people who enjoy math in this way. That's a sign of a kindred spirit, and it's just quite an honor. So thank you.